Hello, my name is Abel Duprat, and I am an undergraduate research assistant at Northern Arizona University. Today, we're going to review some of the general option configuration keys that are available to use with PyBioNetFit. PyBioNetFit is a software package that supports parameterization of biological models that is being developed at Northern Arizona University and Los Alamos National Laboratory. Documentation about the software is provided below. In our previous videos that are available through this channel, we went over how to install PyBioNetFit on a PC running the Windows 10 operating system, how to configure a simple fitting job to run with this software, and how to utilize SPML models through it, as well as the configuration keys that are required to run jobs on PyBioNetFit. Okay. So in the documentation, the fourth section is for configuration keys. And the second to last section within configuration keys is for general options. And so I'm going to select general options. And the first section within general options is output options. And the first configuration key from there is for delete old files. And so by default, this is set to 1. And with 1, there's a simulation folder that is generated while the job is running. That folder is deleted after the job is complete. The other two options for this key is for 0 and 2. When this is set to 2, that simulation folder is still deleted, but then also the sorted parameter text files from the results folder is also deleted as well. When this is set to 0, that means that no files are deleted. The simulation folder and those sorted parameter text files are not deleted. And this documentation does give a warning that obviously if no files are ever deleted, over time that can take up a lot of space on your drive. And the next key that we have below that is the number to output. And so by default, as we see here, there is a maximum of 5,000 parameter sets that are generated at the end of a job. And this key allows you to alter the maximum number that is generated. And so in this example, instead of 5,000 being set for the maximum is set to 100,000 parameter sets that can be generated. All right. For this next configuration key, by default, at every 20 iterations, a sorted parameter text file is generated and stored in your results folder. That file will have your objective functions for each iteration group sorted from best to worst. So if you're running 60 iterations, then at every 20 iterations, one of those files is generated with the objective functions from those runs sorted. If you would like to alter how often those files are generated, you just need to enter the configuration key, like this, at how many number of iterations should those text files be generated. So to show you an example here, I had a job that ran for 30 iterations, and I changed the key to output for every 5 iterations. And so in my results folder here, what I got was 6 of these sorted parameter text files numbered from 0 to 5. And so at every 5th iteration, a new text file was generated for me. And so that's just to show you what that would look like in your results folder as well. And going on from there, we have the save best data. And so in order to run this configuration key, you will just need to enable it with the value 1. And with this key, at the end of your job, one last simulation is run using the best fitting parameters. After this runs, it will save the best fit GDAT file into your results folder. And so let me bring this over. And then just kind of to show you, when I go into my output and go into my results folder, I now have an additional GDAT file that is saved from the saved best data that ran at the end of my last job. And when I open that, we can kind of see here, this will show me the actual data for the best fit for the parameters that I had previously set. And so once again, by default, that does not run, but to enable it, you just use this configuration key with the value of 1 at the end. And so for verbosity, this controls how much information is displayed in our Anaconda prompt terminal. And so the default is using the key 1, and that's described as normal. And the other two options are 0 for quiet and 2 for verbose. And I want to bring my terminal over here to show you kind of visually what that looks like. And so this here was when I had set that key to 2. So this is the most detailed information being shown of each job or each iteration that's being ran for my job. And so for this one, I only ran 15 iterations, but you can kind of see each objective that's being given per population that's ran on each iteration. And so this is verbose, the lot of detailed information in here. And if I scroll up, this here is when I had the normal, when I had the key set to 1 for normal. And you kind of see it was grouping what was being ran in groups of 10 here. So it actually only gave me one line when it was doing the 0 out of 15 and then jumped once 10 were finished. It let me know it was now doing 10 of 15. And so if I had round numbers, if I was running 100 iterations, it would just give me updates 10 at a time. And going up from there, this bit of information here is when I had the key set to 0. And for that was quiet, and I did not see anything until it just told me that the fitting was complete. And so those are just the visual representations of what each one of those keys looks like in the terminal. And so like I said, when I set it to 2, it showed me information and detailed progress updates, gave me each objective for each population that was being ran for each iteration. For 1, it only really gave me grouped once I had about 10 at a time iterations being finished. And then for 0, it just let me know when the job was done, didn't give me any updates or anything like that. And then using that key is shown here for the example, the key verbosity, and then equals 0. So these first two configuration keys go together. They are the Bootstrap and the Bootstrap maximum objective keys. Bootstrapping is a method for determining confidence intervals for parameter estimates based on resampling. The data used in curve fitting is resampled to generate synthetic data sets, each of which are then fit. The setting for Bootstrap determines the number of synthetic data sets to be considered. And that is indicated in this example, where the Bootstrap configuration key is set to run 10 Bootstrap replicates. So then moving down to the Bootstrap max objective. So if this configuration key is set, then each Bootstrap replicate must achieve the specified objective value. If a Bootstrap replicate completes fitting with a larger maximum objective function value, then the replicate is discarded and a new replicate is ran in its place. In this example, you can see that maximum objective function value is set to 1.5. Okay, so going down here, this next key, the Constraint Scale, is a process of weighing the qualitative data versus the quantitative data. By default, there is no scaling. The quantitative and qualitative data are weighted equally. If the objective function of one is drastically greater than the other, you can scale them so that those objective functions will be more similar. So in this example, they're being multiplied by 1.5. And then down here, we have the individual variable rounding. And I am going to open my BNGL and EXP file as I explain this. And so here in my BNGL file, when I come down to my actions, you can see that my simulation runs from 0 to 10, and there are 10 steps involved in that. And my EXP file will show you that my time goes from 0 to 10, so it goes by 1 step. 1, 2, 3, 4, all the way to 10. So let me show you that. And you can see that here, one step at a time until we reach 10. And so my job runs fine in PyBioNetFit, but if I had a time set for 2.6, like this here, and then I had accompanying data to go with it, I would get an error message that the time is not in the simulation output. And it would be correct because, as you saw, I have 10 steps going from 0 to 10. And so with individual variable rounding, what it will do is once it gets to that error message, instead of displaying that for you, it will round this up to the next number. In this case, it would be 3 for my set, and it will continue running the job. So let me take care of this here. And so I'm sure obviously you can put together that this is not an ideal key to use because it can cause the GDAT and the EXP files to display different data or different sets of data for you, and they do have to be the same in PyBioNetFit. Okay, so for initialization, the initial population of parameter sets is generated based off of the key specified for each free parameter. So I am going to open my configuration file here to show you that I am using the uniform variable set of parameters, and I am going between 0 and 10. So these are my set parameters and the range of that parameter there. And so the value of the parameter in each new random parameter set is drawn from the specified probability distribution. So this option only affects the initialization of uniform variable and log uniform variable keys. So when they are enabled, instead of drawing an independent random value for each starting parameter set, the starting parameter sets are generated with the Latin hypercube sampling. And as you can see, by default, we do use that feature. But if you do not want to initiate the Latin hypercube sampling, if you set the key to RAND right there, you will initialize the parameters randomly according to those distributions that I showed in my configuration key there. Local Objective EVA is utilized. All jobs are completed on the core that they began on without being aided by other cores. So this does increase the overall time for a job to finish. As far as enabling this feature, you do just have to set this configuration key to 1. And by default, like I said, this is not utilized unless we are using smoothing, which we'll discuss in a little bit here. Below this, we have the minimum objective. So this will stop the fit if an objective function lower than the selected value is reached. So in this example, the minimum objective was set to 0.01. So if there's an objective function that is found lower than that, it will stop before the set amount of max iterations that were set to ran. So by default, this is not enabled. In those cases, the maximum iterations will run to completion. And if a minimum objective function is set, it will override this by default. So for normalization, we have to both specify the type of normalization we want to utilize, as well as which data sets to apply that normalization to. As we can see here, we have 4 different types of normalizations to select from. We can choose to normalize to the initial value. We can normalize to the maximum value. We can normalize such that each column has a mean of 0 and a standard deviation of 1. And we can also scale the data so that the range of values are between the minimum minus the initial value divided by the maximum minus the initial value and 1. Then the data is scaled by the minimum value after subtracting the initial value so that the range of values is between 0 and -1. But if the maximum value is 0, then the max equals the initial. So once we have picked the type of normalization we would like to use, we need to determine which of our data sets to apply them to. This first example here shows that if only the type of normalization is specified, then that normalization is applied to all of your EXP files. This second example shows that if a colon is used and EXP files are separated by commas, then the ones listed after the colon will be used. So in this example, you will normalize to the initial value for the data1 and data2 EXP files. This third example shows how to specify columns within a data file. This is shown to once again be a colon. Then within a set of parentheses, you have your data file followed by another column, and then you are specifying the observables within that EXP file. So in this example, in the data1 EXP file, the observable columns for 1 and then for the columns between 3 and 5 will be used, whereas for data set 2, the observables var1 and var2 shall be used. So by default, there is no post-processing enabled. If you do want to run a custom Python script that will take your simulation results and run post-processing before evaluating the objective function, you will need to specify the path to that Python script. After the path is listed, you will need to specify the simulation suffixes that the post-processing script should be applied to. In the example here, suffix 1 and 2 are from the simulation itself. So with refine, after fitting is completed, you have your best fit and you do one more iteration using the simplex algorithm to try to make it a little better. So the default for that is 0 where it is not enabled. And so if you would like to enable it, use the command refine equals 1. All right, if we keep going down this page here, we will have the SPML integrator. So this is specific to SPML models, but the SPML integrator allows you to choose what type of integrator to use when running your SPML model. So there are 4 options, and by default, the CFODE integrator is chosen. And the other options are the Runge-Kutta fourth order method, which is shown here by the RK4, the Gillespie, and Euler. If your SPML specifies the use of the SSA method, then by default, the Gillespie method is used. So you can see in the example here, instead of having the default as CFODE, if you type out the SPML integrator, you can choose one of the other methods, in this case, RK4. And smoothing was mentioned earlier. So it is helpful with stochastic simulations. This key allows you to converge your lines by averaging them out and producing a line of that average. So this process is extremely costly and time-consuming to run. So if you remember from earlier, when you enable smoothing, you also automatically enable the local objective evaluation. The default is set to 1. And if you would like to utilize this key, you would have to indicate how many smoothings you would like to run. In this example, it is set to 2. And the last 2 options that we have here are wall time generation and wall time simulation. Wall time generation is the maximum time in seconds to wait to generate the network for a BNGL model. This will cause the program to exit if that number is exceeded. The default is set to 3600. So if you'd like to change it, you just have to type it out like this, wall_time_gen equals the amount of time in seconds you would like to change that to. Similarly, wall time simulation is the maximum time to wait for a simulation to finish. So this can be used for SPML models, but ultimately it will slow down your fitting. If the job hangs for too long without moving, there is a chance that all of the processors can be hung up and the job will stall. So if you would like to utilize this feature, by default, it is set for 3,600 seconds for the BNGL model, and there are no limits set for the SBML models. But if you'd like to change that time, you would just indicate it by the number of seconds here. All right, so those are the general algorithm option keys that are available to you through PyBioNetFit. And once again, this is all found through the PyBioNetFit documentation that we will have linked for you below. So long.